Hey guys, welcome to another episode of Robo Papers. Super glad today to have both Hongyu and Jiahui. They are two of the co-authors from this paper called NovaFlow, Zero Shot Manipulation via Actionable Flow from Generated Videos. Thank you so much for making the time, guys. Maybe as a start, if you can give a quick intro about yourself, it would be great. Maybe Hongyu, you can start first.
Sure. Thanks for inviting us. So my name is Hongyu Li. So I'm a PhD student at Brown. So for this work, is the work I did at RAI with other co-authors, including Linfeng, Yafei, Zui, Jenny, George, and Jiahui as well.
Hi everyone, I'm Jiahui. I'm currently a research scientist at RAI, Robotics and AI Institute, and this is the work Hongyu and I did during past summer, trying to learn from human demonstrations in the videos to teach robots to do zero-shot manipulation.
So let's start it. So this is just like an overview video of what we did. So we first generate a video. For example, this is a purely generated video of a human inserting this yellow block.
It's purely generated here, meaning generated by like WAN or Veo or something.
It's generated by like a pre-trained model. Like we didn't do any fine-tuning.
Okay.
And from this generated video, we lifted to 3D using depth estimation. And with this estimated depths, we can perform 3D point tracking. And we use this grounded 3D tracking result, call it actionable flow, because from this flow, we can directly convert it into robot actions. So we show it can work zero-shot on multiple tasks, including articulated objects as well as deformable objects. Then I think like Jiahui can introduce a bit more about like the high-level motivation.
Yeah, I feel like the motivation of this work is basically we always want to have a generous robot that can do most of the tasks we want without any task-specific training. But so there's the kind of like the VLA trend of trying to use like large quantities of data to train like a generous robot, but trying to follow like the success of LLM and VLM. But I feel there's the biggest gap between a successful VLA and those like VLM and VLM there's the big data gap, because we can learn from like images and text, those web scale data very easily that are readily available out there. But for robot, it's actually very time consuming and hard to get high quality, say tally-up data to get the model well trained. And also it's very easy for those to direct like the new task to be easily out of distribution, even if we're training like the same type of tasks. So that's why I feel there's another trend to trying to create the generous robot. It's just we can use like trying to build a kind of like a modular system to learn to leverage those classical engineering method like MPC or inverse kinematics. But those are like we can generate. But then the gap is that how can we actually translate those from say the videos to get them to speak the language as the robot can understand, is that how can we extract the actions from them to convert them into robot actions. So that's why here I think like here we're trying to build the method that is like the NovaFlow here, trying to extract the videos actions from those videos and make them to be directly applicable direct to different platforms on a robot. Then we can teach the robot to do the actions. Okay, Hongyu.
So the video here we're showing is like it's not I think probably it's not recent, but it's like a video comes from like a Sunday Robotics, right? Like a month or two ago. And I think it's really amazing, like if you're seeing like all these like autonomous skills, and it's kind of really long horizon. And here they also demonstrate some of like a zero-shot generalization capabilities. So what we are interested is what we called like a zero-shot skill here. And by zero shot, like I think I think there are right now like two different definitions right now in the field. I think one type of work they collect demos. Task demos on n tasks. And if this train policy works on n+1 tasks, then that +1 task is zero shot. And there's another trend of work, which, they collect data on zero tasks, which is no data, like no task collection. And somehow it works on some set of tasks. And that's actually what we really want to focus on this task, which is we want to identify a set of tasks that this purely zero-shot framework can directly work. And we want to identify the boundary And we want to say, oh, like why these tasks we can perform zero shot and why others cannot. So I think that's really the purpose of NovaFlow, that we want to identify what kind of tasks that we can already achieve. Yes, amount of the knowledge we can distill from this foundation model, and all these good old fashioned stuff we already know for decades. So that's really what we are trying to do here. So we first started from this classical robotics framework, which there is perception, there's planning, and there is control. And recently, like, people's interest is more on this language thing, and so there's also like a language grounding. How can we ground the natural language into robots' perception as well as planning? So this is like a traditional framework that we're following, and we decompose this into two main components. So one is the task understanding part, and one is task execution part. And also, this is not like what we propose. This like trend of work already doing this, and we just follow this direction. We find this very promising that the input to this task understanding module, is a task description, which in our case it is one RGB image plus a natural language description of the task. For example, you take a picture of the table and say, hand the mug on the rack, something like that. And given this task description, the task understanding module converts it into a task representation. And from this task representation, we have a task execution module, which converts the representation into a set of robot commands. So this is a decoupled way here. There's a line of work following this, but the real difference, and I think the limitation to achieve generalization and scalability, is the task representation. So what kind of representation we want to use is actually very, very important here. And that's the key contribution of NovaFlow. So I want to give and for the task understanding part, it's actually what large models are really good at. For example, what we've seen like in recent years since the success of ChatGPT, right? It like understanding natural language and image becomes super powerful nowadays compared to like 5 years ago. And we know that to understand task better, we need foundation models and large models. And here's some recent works that propose different task representation. For example, code diffuser, like there's also a line of work on this, but code diffuser is a quite recent one. From the back, there's a lot of work from Google where they use code, like Python code, to represent the task. For example, you hand the mug, you have a Python code to first detect the mug, and then you detect the branch, and then you write just a Python code, so on, and to perform the task. And there's also key points. For example, this recap, and also, there's also a lot of works on this direction, which they have this 2D key points, and also the 2D key points is used in Python program to represent this task. For example, you say, if we want to hand the mug on the rack, it will be written as a series of Python program that describes a 2D key point motion. And then there's also work that represents the task using 60 pose. For example, here, they represent this object using its 60 pose. So there are all different task representation out there following this, decoupled framework, which is task understanding and task execution. So what's the problem? So for code, it is not directly grounded in the 3D scene. So we have to combine it with other modules. For example, if you want to describe the mug here, you need to have a detect function. And for the key points, it's not directly in 3D, so that it's not very natural and powerful to represent some 3D motion, for example, rotation or other 3D motion. And for the 60 pose, it's not really generalizable to different objects. For example, like a 60 degree of freedom you can only represent rigid body. You cannot represent, for example, articulated object. Then you have to do like a part-wise, separation. And for deformed object, 60 degree of freedom is not enough to describe its state. So these current representation, we find they all have some problem, and which really hinder the generalization.
Can I ask one question here before we go on?
Yes.
So like,
Yeah.
okay, I mean, I think I know what your answer is going to be, but like, I feel like there's the obvious one of why not just directly predict the trajectory like pi 0.5 or something is doing. How does that fit into this?
You mean the trajectory of the
the actions? Like, why not directly?
Oh, you mean directly
actions?
predict the action?
Yeah.
So that would be, I guess, that would be the other way. That we just not like decouple this, right? You just have like observation in and action out.
Sure. Yeah.
So I think that's really like a thing like people has been debating, right? So I think one problem right now is for vision for purely language model like LLM, that's gonna work because language is like a man-made stuff, and there's everything. Every language is everywhere on the internet. And for VLM, right, there's addition vision thing. But for VLA, you have to also collect like a vision language at the same time. You have to collect action, which you have to collect data. I mean, there's simulation work, but if you want to collect data in physical world, I guess that would be much more expensive than LLM and VLM. And I think like for experiments we have done in NovaFlow, we have tried some VLAs, right? And I don't think zero shot is still there yet. Like I would say you must collect some in-domain data to fine-tune it.
So more scalable, better performance. Is that the kind of?
Yes. So I think if we have like a more like a static setting or control setting, collecting more data seems to show promise for these kind of like an end-to-end method. But I don't think we have seen like any positive evidence showing it's really generalization capabilities like in the wild scenarios.
Okay.
Cool. Yeah. So we actually tried all these like state-of-the-art VLAs in our lab, and we find it's not really like there yet. Probably it will be better like next year. We'll see, but probably not right now. So that's really like kind of motivate us like why studying this problem, which is for these like set of tasks. Can we really achieve it zero shot? So here's what we want to, one way to achieve better generalization is we want to find a better task representation. And here we utilize the 3D point flow. For example, if we want to hand the mug on the rack, it will generate like all the points on the mug as a 3D flow towards the rack. It's a very simple mass definition, which is T by N by 3, where the T is the length of the flow and N is the number of points on this flow. So it can represent all types of motion and also directly grounded in the 3D scene. So when I say all type of motion, I mean not only motion on rigid object, it can only represent like an articulated object or deformable object naturally. So I think that's really an advantage that we see. We can beyond representing these objects using 60 pose. So here we use 3D flow as an intermediate representation between task understanding and task execution. So for this work I talked about, they all use foundation models like VLMs or video models and achieve their tasks zero shot. So the key question we want to ask in NovaFlow is, can we also generate flow zero shot? So here I want to first introduce our pipeline. So starting from a RGBD image and a natural language task description, we first pass the RGB image and the natural language description into a video model. Here we use one, which is an open source model, and Gemini Veo, which is a closed source model. So here is the generated video. It is purely generated.
Could you clarify what it means that you used both? Like, is one for depth and one for RGB, or or did you just try both? Or
so we kind of so the problem was we wanted to use just Veo, but the problem was at that time when we did the experiment, Veo was not like a full release. It only contained partial functionality. They can only I remember they can only generate from an image. But for some tasks, we find if you have a goal image, that can significantly improve the performance and the stability of the generated video. So we also tried that mode. And also one problem was Gemini was very expensive. So by the time we used
$2.
I think it was pretty expensive. I mean, recently their price comes down by a bit, but I think at that time we need to spend like $4 or $5 every time we generate one video, something like that. And when we do all the experiment, obviously we need to generate hundreds of those. So we also tried one, which is an open source video model, and we want to see, if we can use everything as like an open source model, how far can we go? So that's the purpose of using both models. And also we also at that time one was pretty slow, so we also gave like a comparison there. So the first step, we generate a video.
I have a follow-up question. So all these generated videos, so given one static image and then literally, let's say, hang the mug. So do you literally just generate one video and then just take that video as the video to try to do that?
That's a very good question. So the short answer is no. We generate a bunch of videos, and how we gonna do deal with it, I'll introduce probably later.
Okay.
But to your question, we generate videos in parallel.
Got it.
Kind
of a follow-up question. So is the instruction really just something like hang the mug? That's it? Or is it like hang the mug with your hand, with your right hand, or like
that's a good question. So actually we find it like there's some trick here, right? So we've seen a lot of work. They want to generate robot video, but in practice, generating robot video is really, really challenging. First of all, if you see like a Franca arm, it has 7 degrees of freedom, plus you have anti-factor. And if you want every degree of freedom to work precisely, I would say that's a very, very challenging thing for video model. And I don't think right now there's any video model can achieve that. Unless what?
Sorry, doesn't a human hand have more degrees of freedom than that, or human arm?
But I would say they observe like a more human hand video, at least much more than like a Franca video, I would say. But probably like next year it might be. I mean, there's always surprise. But by the time we experiment, we tried generating robot video. It not only messed up with robot morphology, but also it messed up with like object contact and object physics, those kind of things. We ultimately decide to generate human hand video, and because we find it's the most stable option there. So like a hand mug is not actually just hand mug; it's just the only word we can put into this figure. It's actually like a hand mug using a human hand or something like that. And after you using that prompt. For Gemini, this kind of closed source model, and this kind of open source model, there's also like a step called prompt extension. So based on this input image and language, it will just extend your prompt into a better and longer version suitable for the video model. So for Van, there is a prompt template, open source there. And Gemini is, obviously closed source, but there is a staff, right? Like a prompt extension staff. And what is the ultimate prompt that goes into the Gemini model? We don't know. So after generating this video, we first lift it to 3D. So this is through a step called monocular depth estimation. I believe you must know that. And but we all know that monocular depth is a bit magic, right? So for monocular there is no like a 3D geometry constraint, not like stereo, right? Stereo obviously you know the 3D, but monocular there is no way you can know the 3D precisely. So you must have this kind of scale ambiguity, and how to fix that is we have the initial depth image from the initial RGBD image pair. So we use the initial depth image to calibrate the estimated depth video into a metric depth. And we find it actually works pretty well. So once we get the metric depth video, as well as the generated video, we can perform 3D point tracking as well as the object grounding to obtain the 3D flow on our like object, which is mug here. And this is the process of getting what we call actionable flow. So here I want to show like the detailed model we use in the pipeline. So at that time, we were using this model called MegaSam, which was a CVPR 2025 paper. So what MegaSam does is they can convert this monocular video into to estimate the camera motion, the point map per frame, which is super powerful if you think about it, right? So, but for us, we are using like a simplified version of it because we know the camera intrinsics, we know that we know the camera extrinsics, which is identity throughout the video, because we are assuming that camera is static. So we only care about per frame point map. And MegaSam works pretty well because they have a consistent video depth optimization step, which makes the video frame very coherent. And we use another model, which is TAPIP 3D. So TAPIP 3D is further extending MegaSam, which it assumes that we have an estimated camera motion from somewhere, for example, MegaSam, and we have an estimated video depth. What TAPIP 3D does is they estimate the point, which is a point tracker. They estimate the point's 3D motion in the camera frame. So here they represent the camera, the point motion as XYZ. So it's a 3D point tracker. So here we demonstrate how can we generate flow in zero shot using a video model and a perception pipeline. So the next question we want to ask is, if we want to do the task zero shot, we need both modules to work zero shot. For task understanding, sure, we have foundation models, right? Basically, there is like a generation models. We have computer vision models. We can do it zero shot. It's probably not like a big surprise, but what really matter is the task execution part, which is how can we obtain the robot actions to actually do the task. And that's actually the bottleneck of a lot of works, because you need to collect a lot of data to obtain this policy, right? Basically, it's a policy. So what we want to echo here is the good old-fashioned engineering, right? So there's a lot of things that has been working for decades, and we want to remind people that things can work without using any deep learning. For example, here's a video from Russ Tedrick's course at MIT. Even though I think he himself probably not believing this at this moment, but this actually happened decades ago. You have a perching glider here, right? You have a glider and it just hang on this string. If you look at how difficult this task is, and I don't think with VLA or with diffusion policies it's that trivial to do it. So I think this is something that still reminds me of using math and optimization. Some amazing things can still happen without deep learning, right? So I think it's really cool, and the thing behind this is trajectory optimization, right? So we actually we adopt like a similar optimization framework here. So given the actionable flow, we first do the grasp proposal, which is GraphGen from NVIDIA. With a selected grasp candidate, we perform optimization. We formulate an optimization, which is like a trajectory optimization, and then we, with the optimized trajectory, we perform online execution. So here, let me see. Yeah, so here's the term. Yeah.
Sorry, why? So you need the grasp proposal just because like it was a human hand before, so you don't know the exact final configuration to close the grip around the object. Is that why?
Yeah, that's a great question. So yeah, so in the video we have human hand. So for this work, we didn't really want to like exploit that human hand prior. There was a reason that at that time we were still believing that human hand might not work. But later on, we find that it's probably much more stable than what we thought. So later, probably Jiahui will introduce how we incorporate human hand prior at there. But here we just use like a grasp proposal directly from GraphGen. Yeah. So it's actually quite simple optimization formulation. So there's just several standard terms. For example, there's a smoothness cost, there's a rest pose cost, and below terms like a Q start IK and Q end IK is we want the optimized trajectory to follow the actionable flow. So we want to follow the flow at the same time, ensure there's a smoothness. And avoiding collision, and also satisfying the joint limit constraint. So it is a standard trajectory optimization formulation plus the flow following cost. And you might ask, for here it seems like we are still putting this rigid assumption. So what about the deformable object we've been keep telling about, right? That we have to solve this deformable problem, which we formulate as a more general thing, which is model-based planning. So basically here, the F is the actionable flow. We extracted from the aforementioned pipeline, and S is the current position of the points on the object, which is like using a state estimation pipeline. So we want to find a sequence of actions that minimize the future particle position following this actionable flow. So basically, this is just like a tracking controller, right? Which is very very popular nowadays. If you look at the local motion or local manipulation line of work, they are all tracking controller. So here is a tracking controller on the flow. Assuming we have a particle model, here we use Fist-Twin as a particle model. It's awesome, right? So here's what Fist-Twin looks like. And this, you can see an overlay on the captured video. So for example, on a rope, you have a human hand as providing a sequence of action. It will predict the future particle states of this rope. So with this model-based planning framework, we can just design a tracking controller using MPC to perform to calculate a sequence of robot actions to track the actionable flow. Yeah. So that's the task execution part.
Cool, makes sense. On the grasp, I'm curious about the grasp proposal side still. So like you're choosing just one of them. Do you think is that how do you choose the best grasp proposal?
We had some like a very naive thing, you rank it and you pick the best one. But I to be honest, it was really the bottleneck of the entire pipeline. And I told Aditya that the GraphGen is really our bottleneck. But I believe he will come up with like a better work like this year. With first of all, I am really I think this is really promising. For example, we see all these diffusion policy and VLA. In order to do these fancy tasks, I think just ask it to do the grasping. I think it's a very simple requirement, and I think if we have some grasping data set, it will just work more robustly than just having graph proposal. Yeah, so I think it will also it's also scalable, and it will also be solved using data driven. So here's like a quick overview of how we do the task. So we first have an initial image. We use this initial image to generate a video. So this is purely generated video using a pre-trained model. With this generated video, we extract the actionable flow on the mug. So this is the 3D flow that represent the task of hanging the mug, right? So with this actionable flow, we can calculate, we can optimize this robot trajectories using the trajectory optimization formulation we just introduced. Cool. So here, probably Jiahui can introduce a bit more about the experiments.
Yes. So for the experiments part, we basically I think we include 6 different tasks, and those basically spans from like basic pick and place and also articulated objects, and also we tested on different embodiments, not only the Franca arm but also the spot. It's not really mobile, but it's at least it's like on a mobile robot platform. So here we show like the success rate out of 10 trials on each of the tasks. And for all of the baseline here, that's AVDC is basically computing with, for AVDC and Bitbot, though those are, we consider zero shot because AVDC basically computes a 2D optical flow and directly apply that onto, to turn that into actions. And then Bitbot is also trained on like, kind of like the big, large models to directly get get articulated objects working. I think that's the only thing it can really do. And those with demonstrations, DPR, diffusion policy, that we trained on 2 different variants. One is with 30 demonstrations and one is with 10 demonstrations. And there's the inverse dynamics model. Then we also trained on 30 different demonstrations. And could you go to the next slide? I think for AVDC here, basically, I think the biggest bottleneck is that the optical flow is basically 2D, so it lacks the kind of like the 3D awareness. So that's why it can fail on a lot of the tasks. And then for, do you want to, yeah. So for Bitbot, basically that's what I'm saying. I think it's only capable of opening the drawers because it's trained on like human object interaction data set, and there's very poor understanding of the object to object relationships that it has never seen before in a training data set. And then for all of the diffusion policy, we collected data for each of the tasks, but since we didn't really just follow our training data set to actually curate our testing set, so most of our testing set are actually out of distribution compared to our training data set. So that's why most of the the DP won't work, even no matter it's 30 or 10 demonstration, it won't work on most of our trials. And lastly, for inverse dynamics model, I think it's big because there's like a huge domain shift between like the real video and the generated video. So because it was trained on just like the real demonstrations, I think that once we fit in like the generated video frames, it's also considered out of distribution. So that's why I remember like for IDM, it's mostly just all zeros on all of these tasks.
Yeah, so I want to add something like for IDM, so which is inverse dynamic model. It was originally like proposed in Elon's work called UniPy.
UniPy, yes.
Yeah, so the reason why it worked pretty well in that work was they trained the video model as well as the inverse dynamic model using the same set of collected data, which is not the case here because we used like a pre-trained model, like a one. So which that creates a domain gap because the video model and the IDM, they have a different set of training data. So that creates this domain gap between the real video and which is IDM is seeing and the generative video, which is a one or Google video. Cool. Yeah.
And I think of it here are some of the like the basic walkthrough of like the whole pipeline. Given the like initial image, we generate the video with the like the action command. Then we do the 3D, lift it to 3D, get the depth estimation, then lift it to 3D and get the actionable 3D flow. That's the real like execution on the gripper. This hasn't been accelerated. Yeah, I feel this is like the most interesting task because it requires like relatively higher precision than the previous pick and place task.
Yeah, because the reason why we designed this task was I was really suspicious if our pipeline can work. Because if you remember, the entire 3D part relies on the monocular depths, which I think this thing is really not reliable. So this is why we designed this test to test, how accurate it can handle. And turns out pretty well.
I really like this task, actually. Oh, sorry. I was going to say, I really like this task. It also looked like the human video, the generated video of the human hand, not the human video. But that one looked kind of fake. I guess it didn't quite look like it had the object grasped. So it's interesting that it actually gets to work here. This is nice. Okay. Sorry, go ahead.
And this is our we tried on one deformable object, pushing the rope.
So we ask, so our prompt is like a human hand push the rope to straighten it or something.
Doesn't this make the objective a little bit harder to track because you have the 2 points moving out? How does it rectify? How does that work?
Yeah, so I think it somehow works. Like I don't know.
There's more points moving, so it's fine, or they all balance each other out, or something.
Yeah. It's actually. It means that the generated video is actually somehow physics realistic, because that's actually what you expect from pushing this rope from the middle. And we actually made a few assumptions, and I want to be clear. So first of all, we assume we have the deformable objects dynamic model. Even though we don't have such foundation model for deformable dynamics, but we are going to have one because I'm building one. And the second assumption is we are simplifying the contact sampling here, that we are not doing the contact sampling, which all the MPC should do, which we just use where the human hand makes contact with the object. And we directly use that as the contact point for MPC. Here is directly executing the action sequence calculated from MPC. Actually, you can see there's a bit discrepancy between the final rope state and the video state. That's because there's some gap from the dynamic model. The dynamic model is not 100% accurate, and that's where the discrepancy comes from. And also one big advantage, since Chris asked, why not just VLA? Here's another reason why: because our pipeline is naturally cross-embodied, right? We can directly use this pipeline on a different robot, like the spot we have here, and it's just also work exactly the same. So when we did this experiment, we didn't change anything, we didn't tune anything. It just works directly on the spot, right? And I think this is something truly amazing, and like an end-to-end model cannot do at this moment. Maybe in the future. Yeah. So this cross-embodiment, capability is something that also is one of the advantage of using this modular framework. So you might think, it's probably too good to be true. Just like what Michael was asking, how is this video gen working, right? So one technique we found was using rejection sampling. So for example, here we show generating 4 videos simultaneously. So imagine we have 4 GPUs, and on each of the GPU, we have an entire pipeline running NovaFlow on each GPU. Then we have 4 NovaFlows. And we visualize the final result of each NovaFlow and project it back to the 2D image. And this is what it looks like. So here's the flow image. And we concat the flow image all together. So on the top left corner is the seed we use to generate these videos to give some randomness. So by concatenating all the final flow image together, we pass it to a VLM here, along with the prompt, help me evaluate which flow image is the most reasonable one. Their IDs are marked on the top left corner. The flow represents the object motion from one place to the other, and the task instruction is, which, we put the task instruction there, which in this case is open the drawer. And the VLM will just do the work. It sounds a bit stupid, but somehow I was really surprised that, for example, Gemini and GPT we tried, they worked pretty well, like in this case. So it actually becomes one of the most important steps in the entire framework that provide or somehow provide a much higher success rate in the end. It helped us filter a lot of failures resulting from like a inaccurate flow. For example, there can be like a different failure modes, like video hallucination, like a tracking failure, or there's a grounding error. There's a lot of failures which can, you can have a lot of failures in this kind of pipeline because it's a modular framework. And actually, that's the biggest problem of this modular framework because every module can have problem. So with this final rejection sampling step, you can filter out most of them and keep the candidate that is success ultimately. Okay, so here's Jiahui's part.
Yeah, I think basically this is kind of like a follow-up work. We're trying to extend NovaFlow to do like longer horizon multi-step tasks. That's actually because in the first of it, I was always interested in kind of like doing longer horizon tasks. But the problem is that for now, I think the video model is not able to first, if you're given a longer, higher level of a longer horizon task, say build the stack the 4 blocks onto each other or things like that. There's no way like the video model first can naturally decompose the task and trying to generate a very long video to be both like spatially and temporally consistent. So that's why I feel there's the need to first try to build a planner that use NovaFlow as like the execution level, but on top of it, trying to build a planner first decompose the high level tasks and use NovaFlow to accomplish each of the sub tasks. So that's why that's how we want to do the extension. But the problem is that I think the interesting part here is that we're trying to not only use the object-centric flow, but also we're trying to use the hand priors inside the generated video to do that. And so here I'm not gonna trying to reveal a lot of the details, but this is one of like the most difficult tasks we've tried in our work. It's the functional manipulation benchmark.
Should I start playing the video?
I think we have, you can play, but we also have like in later slides for each of the steps.
Oh, okay.
If you want to play it, you can go to the next slide for each of the steps. First, so it's basically a 4-step multi-object assembly task that will require first a very smart planning, because this is kind of like a variant that's of the original task that will require first to put in a long yellow bar inside it, and later on trying to gradually put the yellow the purple, green, and blue blocks in the far side in whatever order, but the yellow one should be definitely come in first. Otherwise, it will block the way to get it into the central long groove. So I feel like for most of the time, even though we use the VLMs to do this task decomposition, even though the VLM's IQ may fluctuate a lot of the times, but in general, it was able to actually figure out I need to put in the yellow block first, and then follow whatever later order to put in the rest of the 3. So the high level task decomposition is not the bottleneck, but the real challenge here is trying to do it with sub-millimeter accuracy. So here we can first see the task. This is the generation, and we put in. If you go to the next one, this is a step 1.
So the task planning is all done by VLM, by ChatGPT or Gemini, something like that.
On the left side is the generated video, and the right side is the real execution.
What's the recovery? What?
Yeah, because we're building this as a closed loop system, so we have a VLM to check at once each step is accomplished, we have the state verification check. So is this is this a success or failure? If VLM said, oh, it's actually a failure, then we trying to generate a recovery video and trying to recover to let the robot to recover the current failure state to the goal state predicted by the video. I think you can go to step 3. This is actually the slide order is kind of wrong. Yeah, and then step 4. Now you can see here in step 4, because the purple one is actually the longest from this its starting position to the goal position. So actually, it's very hard to actually directly get it in the first trial. So that's why I actually encountered an error here. That's it didn't really directly go into the groove, but actually sits lean back onto the green one, and then so that's why we query the VLM. Actually, this is kind of like a dexterous. It's not just read grasp. It's actually we prompt the VLM to say, can you do with a poking motion to actually generate the to generate recovery video. So this is the generated one. You can tell there's a red star on it. It's
Is
actually
this a generated video?
generated video. So that's like
amazing.
the BLM first they say, oh, you should actually poke at the red star location with inward poke. And then we can use like the hand priors to directly poke it instead of trying to regrasp, because this one also requires higher precision. If just doing the regrasp, probably it will still fail at the same place. So do a regrasping to get it recovered in the shortest amount of movement is actually like the smartest way to recover that. And then we're actually able, this is from a side view, so you can see like the poke more more clearly. So that's why we directly follow like the index finger trajectory to poke it and recover it back to the goal state. I feel that's like the more interesting part of the recovery.
Sorry, so this action of poking, is it suggested by you or suggested by
the VLM? So I was saying, could you actually recover it in the shortest path instead of trying to regrasp it, take it out and re-plug it in, and then say like with one finger. The only clue I was giving to the VLM is just with one finger. And then VLM say, oh, probably poking at like the red star place. But I feel like the actual hard part is actually trying to generate this video. And I was actually need to manually iterate for the prompt several times in order to get it perfectly accurate to follow like what the BLM was suggesting.
Do you think that's something that'll be automatable in the future? Like, do you think it'll be able
Yeah,
to...
I think that's definitely, because we just want to show there's this like interesting, like more dexterous recovery mode compared to just do the normal regrasping. Because for normal recovery for regrasping, it's basically still the same kind of action suggested by VLM it's just at a different starting state, trying to go back to the loop to generate the video and then do the execution. If you go to like there's a teaser I think the teaser slide, like the hero image slide. Yeah, this is basically our pipeline. And then in the first bit, we have a higher level video language planner to generate like the video, first to decompose the task and generate it into each of the stop task videos at the very top row. And then for each of the tasks, we extract we can extract the object flow, but also we can extract the hand flow. The hand flow here is basically defined as a sequence of the hand pulse. We basically use hammer to extract the hand pulse and apply some scale calibration, because for now, like the video model is still not able to actually generate spatially consistent hands. Sometimes we get giant hands when it gets closer in front of the camera. So that's why I need to apply some sort of calibration to do that. So, but in general, once we get like the sequence of hand flows, the sequence of hand pulses, we can still compute like just like the object flow to get the series of relative transform between the different hand poses to apply that to the gripper. So that's why, and also the motivation of trying to switch from object flow to hand flow, to me, I ran into actually, I would say 3 reasons. The first is that the human video actually the videos using the human hand is relatively stable because there are tons of like internet data that like the video model knows it pretty well. The second is that there's usually when there's like in the object flow, if you get the object, like the object is heavily occluded, there's actually less points or no points you can actually track. It got cut in the middle, and usually the computed object like the object poses like the flow poses are really not really stable and cannot be directly applied to the gripper. The third one it's actually that for those of the like longer horizon, more complex tasks, actually these are, especially like for this FFmpeg, it's not like the canonical object shape or poses, especially during recovery, that the monocular depth estimators, those have seen in their training data. So sometimes like the depth predicted in the middle are actually very bad. So but for the hand flow, the hand poses are relatively more stable, and also for calibration of the hand poses, we usually just need the first and last depth image to do that, so we can kind of bypass the flickering depth in the middle coming from those monocular depths. So that's why I feel in general, like when we cannot solve it using like the object flow, usually the hand flow will also provide a very stable way to also trying to just let the grippers complete the task.
Yeah, I mean, it also feels like it has more potential for like precise adaptation or manipulation, like your pointing example here, or like in the rope example, it probably would have been useful to say exactly where to grab the rope to straighten it out, for example, or something like that. No, that makes sense. Okay.
Yeah, yeah, finally we here have a table of the overview of the models, each of the models we use in different modules. These are definitely replaceable as we have more advanced models coming up in the future, and there's also a runtime analysis. So we call our later the work is called NovaPlan. So here for the video generation part for both NovaFlow and NovaPlan, we use the both one and VO, but there's a slight upgrade in terms of the version. And also in NovaPlan, we deployed through the config UI. So I think there's a kind of a boost in the runtime. Actually, in the first one for NovaPlay at that time, 2.1, we need to spend about 9 to 10 minutes to get the video, though in parallel, 8 videos in parallel, but it's 9 or 10 minutes. But for now, for NovaPlay through config UI, we can literally get 30 seconds to get all of the 8 videos in parallel.
Yeah.
Using
So yeah, actually we find there's a optimized model for one. Shout out to Light X2V, which they provide a quantization plus distillation version of one, which greatly improves the speed of this model from 540 seconds to 30 seconds, which without any obvious a reduction in the performance. So it's awesome. and that's something we observed recently. And yeah, so it is called Light X2V. Yeah, and I didn't know this quantization or distillation thing before, but now I think it's makes all these runtime thing more promising. Yeah.
And then for molecular depth estimation in the first place, like Hongyu just mentioned, we used to use Megasam, but it's also very cumbersome. And later in NovaPlan, I actually tried different models, and each of them probably have their favorite theme, but most of them will perform kind of similar on most of our tasks we've tried. Those are Moji2, Depth Anything Free, and also Hongyu World Mirror. This usually takes about 3 seconds to get the full depth estimation for 41 frame 320p video generated by one. And then for segmentation versus SAM2, then we upgraded to SAM3. Usually I think the overhead here is not that significant. And then for 3D tracking we use just Tappy 3D, and also the Tappy 3D now in NovaPlan also is deployed for config UI. So I guess it still gets kind of a slight speed boost. So from end to end, NovaFlow used to be 730 seconds around that time, but now NovaPlan takes about only 40 seconds end to end. So I don't know, but I don't really know how fast do we actually need for online planning, but at least this is a big step forward. Yeah, so probably there are also, I feel the biggest bottleneck here is still the video generation part. So I feel it's actually very promising to actually put the whole realize this online replanning with the fast advances in video model.
Yeah, so I think there's a lot of reasons that we believe this can be further speed up to 4 seconds in our next upgrade. With 4 seconds we can obviously do a lot of things. For example, online replanning. And I think that would be truly amazing at that time. But also for this,
from 40 to 4 seconds total for the whole loop, so generating video and everything.
Yeah.
Okay.
Yeah. I think that's actually a totally doable thing. For example, we see a trend right now, to distill this kind of modular framework into a smaller end-to-end model. Which that should also apply here, which we will then see another great speed up at that time. So with that,
so you're thinking by distill you mean take all of these different pieces and just directly supervise the output to have one single model that's much faster.
Right,
Okay.
right, exactly. So I we've seen some flow model out there yet, but they are not scaled up yet. But I think if we can scale up and make it more efficient, it's definitely doable and can be run in an online manner. But also, this is just an online planner. It's a high level planner that for the low level robot execution, we don't have to run this plan every cycle. We can just follow it, which for example, in the old days navigation stack, we have these global planner and local planner. So I think that's in that formulation, our plan can a flow can serve as a global planner. So I think the runtime I'm not really worried about. I think it will keep improving over the next years. So I think that's the end of the talk. Thank you for inviting us again.
Yeah. Well, thanks for
Yeah,
doing this.
Yeah, thank you so much for coming on. I have one more, I guess, follow-up question on like so you guys basically, at least for this work, you generate like, let's say, 4 different generated videos, right? Have you come across any instance where like none of the 4 videos actually work? It's always the case that at least one of them is usable.
I see. So actually, in reality, we didn't generate 4. We generated 8 or sometimes 16, depending on how many H100 we can grab at that time. But it's embarrassing in parallel. You can, if we can grab like a 30 GPU, you can just run 30, and obviously the success rate will be much higher.
And you say that the VLM judge subsequently is a decent judge.
It's quite decent. I would say it's quite decent, and I think there's a reason we can believe that part will not be the bottleneck. If we find it unreasonable, one thing we can do basically is there's a lot of like open source VLM we can just grab there on Hugging Face. You can just like fine tune something like with some post training, give it on flow evaluation task. I think that's totally doable thing.
So I guess at its limit, like how well, I mean, you already mentioned you think that throughout, like it's dropping from 700 something seconds to 40 seconds, and then eventually a few seconds. Yeah, so I think that's probably going to be the trend. But like, do you see any fundamental bottleneck to this like pipeline? Like, where do you think it was like things will stop working? Like,
yeah, that's
gonna improve, right? Obviously.
I think that's a great question, and it really goes back to the very beginning. When we talk about what is the purpose of this line of work, which is really we want to find a boundary, what we can do zero shot and what we cannot. So first of all, the bottleneck. Where's the bottleneck? I think right now is the unfortunately graph gen from NVIDIA. But I totally believe like in Aditya's team they will make it better over this year and probably next year. And then is the MPC part, which MPC really relies on dynamic model. So there are 2 things. One is the dynamic model. We must make sure dynamic model work. Then it's a reward model. Right, reward function, which NovaFlow is a reward. We are the reward function. So we want a generalizable dynamic model, which is the world model, and everyone's talking about it. I think there's a very reason to believe that we will have before we have a generalizable VLA, we will have a generalizable world model. That's my personal belief. Because I think for a world model, it's just we can get the data from everywhere. I think the data we can get to train a world model is much larger scale than training like a policy model. So with the world model, for example, recent work like a point world from Stanford, I think it's a great example. Or it's also from NVIDIA, right? It is a great example of these like a scaling up point representation for dynamic model. They haven't open sourced it. We've been talking about this, but they are still in the process of open sourcing. But I think it will be very exciting, to combine the generalizable point-based world model with this kind of point flow as a reward function. And I cannot wait to see, what this synergy goes.
So you're specifically talking about like the action conditioned world models, not like the dream gen kind of like language conditioned ones, right?
No,
you kind of already have a world model in that you're a video model, right? Sort of.
Yeah, exactly. Yeah.
Okay. So do you think that kind of approach where you have like these 2 different components, do you think these sort of modular approaches will always do better at generalization, in your opinion?
It seems like to get each module to be generalizable, it will be definitely much easier. But I think ultimately VLA will be generalizable. But how long will it take? I hope I hope we can build some like data flywheel with this modular framework that we can start doing some tasks with confidence. And once we start doing some tasks with confidence, we can generate data. For example, this kind of flow, like a NovaFlow, we can do some automated data collection already. With this more scalable data collection thing going on, we can collect more and more data that can feed into this more end-to-end policy. So I think that sounds like a more promising interesting thing to me. At least in short run, I think maybe modular will see better performance.
I'm curious, so let's say you use this kind of like WAN or like VO to generate these videos, and you can do 4, 8, 16 or whatever GPU you can throw at it. But then ultimately you actually will deploy and then actually see how it goes, right? So the real video, the thing that actually happened, how do you think we can make use of that particular real video?
Oh, you mean the real execution, like a
Yes.
video? Yeah.
'Cause
So
right now
like
you
a
don't
one
do-
way,
Hmm?
yeah, one way we can use it is to close the loop. I think like Jiahui, introduced in the extension, where we use this actually real video to identify the failures. And once we identify the failure, we can go into a closed loop, right? We can identify where the failure happens and how can we recover from the failure. I think that's one way. And another is, for example, I talk about how can we in the future we can distill this like a modular thing into end-to-end thing. And I think that's when we can use this like a real world collected video. But at that, I think we were like a bit conservative of using our in-domain data, because I was believing that if we just don't use any in-domain data, we'll never overfit. Like if we just don't train anything, we'll never get an overfitting issue. I think that's one way I was like thinking about this problem.
So on that note, or on a similar note, maybe an unrelated note, actually. So as these video models improve, like I expect there to be more robot data in them, and them to get better at robots. So do you think that if you could like directly predict the point flow on the robot model itself, that would make much of a difference here, or like would that make your life easier? I don't know. Let you get rid of grass gen? I don't know.
I see. Yeah, I think it's really like a different research team have different philosophy. I've also seen a lot of great work from other teams that they are predicting like either like a robot video and convert robot video into robot actions, like using inverse dynamic model. Or there are also teams that predicting flow on the robot and convert the robot flow into robot action. I think these are like a really cool work. But I think so far I haven't seen like a very promising thing that saying video can generate robot action zero shot. And I think another way I was really thinking about this is what do we really want from this task? I think what we really care about in these tasks is how object moves. Probably not how robot moves. I mean, robot moves is just one way to bring us to the object, like an object motion we desire. And there can be different ways. For example, we talk about this cross-embodiment problem, that if you have an embodiment specific thing, it might not be that trivial to generalize to different embodiment. But, anyway, maybe we care about it or maybe we don't care about it. I think it totally makes sense for some application that you don't care about cross-embodiment at all, right? For example, like your business, you just want to make it work on your robot. I think it totally makes sense. So I think once we have a more decided those kind of setting, probably like a different choice will make more sense.
Makes sense. Any other questions, Michael?
I think for the VLA thing, I might change my mind if one day I just, Hugging Face download some model on our like a Franca setup, and I'll just give it a language. It just work. And at that time, probably I'll change my mind. I'll say, VLA is already the future, but we haven't seen such thing, so far. We try some recent famous VLA models. I won't give the name, but there's a bunch out there.
Yeah.
Unfortunately, like none of these can just work directly, and you have to still collect some task-specific demos to post-train it in order to make it work.
Yeah, I think that was one thing that stood out to me about this paper was that there's not a lot of people doing zero-shot stuff. Well, I think right now it feels like there's a lot of these VLAs that require lots of.
I think people's expectation on VLA is zero-shot.
Yeah,
but to some degree, I would say.
Yeah.
And I think one very surprising thing that I want to say about this entire NovaFlow is that we use the exact same set of setting for everything you see. For every task and also the spot experiment, everything is just the same. Like we didn't change anything. So I think that's actually a very like interesting thing. And actually it shows you like what kind of like a robustness we can expect from this framework.
So I suppose as this worm get better, longer, even like it seems to me right now some of these tasks are pretty short. Like your general videos is like maybe 2-3 seconds. I imagine they will get pretty good at longer and longer horizon thing, like, maybe fold a very complicated, like, I don't know, shirt or something like that. And so do you think this should work once this pipeline will continue to work?
You mean if we want to apply it to longer tasks?
Yeah.
Yeah, so I think there are like two ways. So one way is like what Jiahui introduced, that right now we have this hierarchical planning framework, that we have a high level planning to do the task decomposition, and for each decomposed subtask, you do like a video generation, so that we can break down a very long horizon task into several video. So I think that's one thing. And the second thing is I think very promising like in long video generation. So right now we've seen a lot of progress in this direction, and I think it will be going much better in 2026. For example, if we see this back in like a year later, maybe long video generation has already been something that people has already start using it. I think that's totally possible. And at that time, maybe we can just with just one video generation, right? We can do the entire long task. Both are like valid options out there. And so I think there's no reason we believe this thing cannot solve long horizon task.
Yeah, really, really very cool, man. I guess if you continue this trend, no one needs to do more tally-up data collection, maybe.
I don't know, but like all the capital are they bet on this data collection and VOA. So I don't know, but
I mean, lots of capital
I
also
hope
world models to prepare. So
yeah.
I do think certainly the world model stuff, like it just take advantage of so much more possible data. I think that's why it just generalize a lot better.
Exactly. So that's why I'm currently building a massive, high quality, deformable dynamic data set that we will train and support like foundation models on predicting such like a dynamic deformable object in the future, which I think that's really gonna work like in a truly zero shot manner.
Cool, very cool. Yeah, I guess we are wrapping up here. Usually the last question we like to ask Hongyu and Jiahui is have you guys come across any like recent papers that you want to give a shout out to, that you think is really cool? It doesn't have to be role model, it could be even
so each of us has a chance to shout out.
Yeah.
You can go
course.
first.
Okay, I'll go first.
I feel like we read very similar set of papers.
Yeah, I'll first shout out to Jiahui's latest work, NovaFlow. But anyway, I think I'll probably like I'll say like a point world from Wenlong Huang at Stanford and NVIDIA. I think that's a very cool work, and that will be like within the this entire framework of model-based planning. That's a really cool work. Yeah.
And Jiahui?
I would say recently I've been talking to people working on mesh generation, SAM3D. I would say that's kind of and also for that one, we can also use that to get more robust, selection as well. Yeah. Because for now, I'm looking at how to further improve the grasp. And also for that one, we even get pretty good meshes of the object, and then we can probably propose better graphs on top of that.
We'll try our best to get some of these authors to come on as well.
Yeah, I mean, I actually think okay, that's great.
I'm sorry, Chris.
Oh yeah. I think Point World's coming on sometime soon. All right.
All right. Okay. Cool.
Yeah. Well, awesome. We'll see. Yeah. We'll see. That's all right.
Okay.
Thanks. Yeah.
That's cool. Yeah. Yeah. We definitely, this world model thing is a big trend. Like we can just tell that the recent episodes is a lot of world models and all like trying to do zero shot and decent success rate. So very generalizable. Especially in your case, it's cross-embodiment because you just simulate the hand and then do the object flow instead of like. So I think that's quite cool. Yeah, really cool work. Thank you so much for making the time coming to share your work. Yeah,
I really like papers like this that are full of interesting ideas that are different, I think, from like the accepted, I guess, wisdom of like the VLAs. So it was a lot of very cool stuff. Yeah, thanks for
inviting us.
Yeah.
Thanks for inviting us.
Cool. Okay, cool. All right, see you guys next time.
See you.